Good morning. Let me know if the audio is clear. Good morning, all of you. Is the audio clear? Fine. So let us start the subject. Let me start with the date today. Today is 10th of October. Yesterday we have discussed some fundamentals of flow through pipes. Let me quickly recapitulate within 5 minutes what all fundamentals we have seen. Let me mention over here. So this particular slide is the revision of yesterday's class. Very important slide. The first thing you have seen over here in the concept of flow through pipes, that whenever you're having a steady and fully developed flow, you're going to have some equations valid for every flow, regardless of what Reynolds number you're going to have. Now, what are these equations? The first equation is the governing equation, which says that R into minus dP upon dx is equal to d upon dr of r times tau. This was the first point we have discussed. The second point was regarding this minus dp upon dx. We have proved that this minus dp upon dx is also equal to delta p upon L is equal to a positive constant, wherein delta P, please understand, does not represent change in pressure. Delta P represents drop in pressure. So delta P over here is drop in pressure. Delta P over here is drop in pressure. Drop in pressure basically means initial pressure minus final pressure. Initial pressure minus final pressure. What would change be? Change is final minus initial, that we are not seeing. We are looking at drop because we are having minus over here. Therefore, we are looking at drop. Now coming to the third point. Achha, in this only we have one more thing mentioned. If you remember, the value of head loss is equal to delta P divided by gamma. Coming to the third point is the concept of shear stress. Shear stress is equal to minus dP upon dx multiplied to r by 2. Then you have something known as wall shear stress represented by tau naught, which also happens to be the maximum shear stress. The value of this thing is minus dP upon dx multiplied to capital R by 2. Coming to the fourth point we are having over here is the concept of friction factor and friction coefficient. The value of tau naught upon half rho v square is equal to friction coefficient represented by F prime. And 4 times friction coefficient is equal to friction factor. In the case of flow through pipes, not laminar, in the case of flow through pipes, this friction factor is called as Fanning's friction, this friction coefficient is called as Fanning's coefficient of friction, and the friction factor is called as Darcy friction factor. Coming to the fifth point is regarding a particular imaginary velocity, which is known as shear or friction velocity, represented by V star, the value of which is equal to root over of tau naught by rho, also happens to be V root over of upon 8. This is the value. Lastly, a very, very important equation, extremely important, is the equation called as Darcy-Weisbach equation. The value of major head loss in every internal flow through pipe, as the flow is going to be steady and fully developed, is given by FLV square by 2GD. Also, in terms of discharge, if you look, it is going to be 1 by 12.1 FLQ square by d power 5. These are the values we are having. Again, over here, the value of F is basically Darcy friction factor. Some people have a habit of writing it as 4F. It is same. You are writing 4F. Same value I'm writing as F. Okay. So all these things we have discussed yesterday. These points are extremely important points. If you know these points, the coming topics are going to be very, very easy. Now let us start today's topic. Today, if you want, you can take a snapshot very quickly of this particular slide. I hope you have memorized all these things by now. I was expecting you to do so. Okay. Quickly take a snapshot of this particular slide, and then we are going to start the first chapter under internal flow, which is known as laminar flow. I'm starting the first topic now, which is known as laminar flow. Laminar flow. Importance wise, not that much important, but sometimes question, just appear from this topic. 2 years back in Civil Gate, 1 2 mark question appeared from here. Likewise in mechanical also, not that much frequently, but they can just appear. Okay. And I regard this particular chapter as the easiest chapter in entire fluid mechanics. There is no chapter as easy as laminar flow. Easiest chapter in entire fluid mechanics. Okay. First of all, let us talk about some theory in this particular slide. This entire slide will be theoretical slide, important for IAS. This particular slide will be important for IAS. Gate, not that much important. You won't have theoretical questions coming from Gate. First thing, we are going to write a definition of laminar flow. How do we define this laminar flow? Laminar flow comes from the word lamina. Lamina basically means sheet or plate. You might have heard of the word lamina even in the subject of strength of materials, is it not? In strength of materials also, you are having the concept of lamina, moment of inertia of lamina, and all these things. Laminas basically mean sheet. Now, what is the concept of sheet in a flow? The concept of sheet in a flow is when a laminar flow takes place, the fluid particles are going to align themselves in the form of sheets or layers of fluid particles. And these layers are going to have some relative motion. Imagine the layers are having some relative motion. Okay. Such that the particle from one layer does not intermix with the particle in other layer. So the layer is being maintained over here. That particular flow is known as laminar flow. So I can write laminar flow as a flow in which layers of fluid particles layers of fluid particles slide over one another with relative velocity relative velocity 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 such that no intermixing takes place. No intermixing takes place. In laminar flow, intermixing of fluid particles is not allowed. In laminar flow, intermixing of fluid particles is not allowed. Okay. So this is the definition of laminar flow we are having. After having defined this laminar flow, okay, after having seen the definition of laminar flow, the next thing we are going to discuss now are some characteristics of laminar flow. This is from where questions can appear probably in your IAS examination. So this is characteristics of laminar flow. Characteristics of laminar flow. Let us look at the various characteristics of laminar flow. The first characteristic of laminar flow we are going to have. Now you see, Layers of fluid are not intermixing at all, or the fluid particles are not intermixing due to domination of viscous forces. If viscous forces are significant or they are dominant, then laminar flow will take place. This can happen if the kinetic energy is less, and eventually the Reynolds number will be less. So first character is relatively low kinetic energy, low kinetic energy and low Reynolds number. Yesterday we have discussed Reynolds number. So this is the first characteristic we are having. Second characteristic. What is the second characteristic of laminar flow? Intermixing is not going to take place. Intermixing of fluid particles between the layers doesn't take place. Intermixing is not going to take place. Third point. Now you see, if intermixing takes place, then there is going to be collision taking place. If collision takes place, then velocity will randomly vary with respect to time. So therefore, in the case of laminar flow, velocity of a fluid particle doesn't vary with respect to time, doesn't vary with respect to time as long as the flow is steady. As long as the flow is steady. So if the flow is steady, velocity of fluid particles is not going to change with respect to time. Fourth point over here. Fourth point. Now, laminar flow, which is having different velocities at different layers, is eventually going to become rotational. Very important point. So rotational flow. Rotational flow. Fifth point over here. Shear stress can be obtained by Newton's law of viscosity. Shear stress can be obtained by Newton's law of viscosity. Law of viscosity. That means whenever you want to calculate shear stress, you can also look for Newton's law of viscosity in order to get the value of shear stress. So these are some primary characteristics of laminar flow. Okay. Apart from this, you'll have some more characteristics which you'll understand once we enter into turbulent flow. Once we see turbulent flow, you can differentiate better between laminar flow and turbulent flow. Excuse me. One moment, please. After having discussed this thing, after having discussed this, let us now talk about some examples of laminar flow. Okay. Examples of laminar flow. Some examples of laminar flow. Now, you see, laminar flow actually is quite a rare flow. It is not that much frequently, observed flow. It is not. It is going to be mostly rare flow only. Okay, because in order to get the Reynolds number less than 2000, in order to get Reynolds number less than 2000, either you are supposed to have, a highly viscous fluid, or you're supposed to have a very, very small diameter of velocity. So these examples are going to be very specific, very rare examples. The first example I'm going to mention over here is flow through, flow through extremely small diameters, like syringe needles, capillary tubes, etc. Apart from this, you can take flow of extremely viscous fluids. Imagine you're having extremely viscous fluid flow. Okay, extremely viscous fluid flow. What are the examples of extremely viscous fluid? The flow of honey, flow of grease, all these things can be laminar flow. Please remember one important note, that flow of water is going to be mostly turbulent. Water is going to have mostly turbulent flow. The reason is water has extremely low viscosity. Okay, the viscosity of water is in the order of 10 power minus 3 pascal second. With 10 power minus 3 pascal second in the denominator, to get less than 2000 as a complete fraction is quite difficult. And again, density is equal to 1000. Okay, so therefore, mostly with water, please make a note of this thing. Mostly with water, you're going to have turbulent flow only going to take place. Laminar flow very rarely takes place with water. Okay? So whenever you see questions wherein water is flowing and you have to make an assumption what flow it is, straight away take an assumption that the flow over there is going to be a turbulent flow. Chaliye. Let us now move further. After having discussed all these characteristics and examples of laminar flow and all, let us now move further to the problems which appear in our examination. We are going to have a set of 4 types of problems. The first category of problem is known as laminar flow through pipes. First category is known as laminar flow through pipes. Second category is known as laminar flow between parallel plates, fixed parallel plates. Okay. Third category is known as laminar flow between one plate which is fixed and the other parallel plate which is moving. That is called as squid flow. And the final category is known as creeping flow. 4 types of flows we are going to see. So once we see 4 flows, then we are going to have some problems taking place. So let us now move further. Look over here. The first topic over here is laminar flow through pipes. This topic over here is laminar flow through pipes. The first topic is laminar flow through pipes. This happens to be the most important of all topics in this particular chapter. Mostly questions appear from laminar flow through pipes whenever they appear from laminar flow chapter. Okay. So now what I'm going to do is I'll first of all start with a diagram of a pipe. Imagine there is a particular pipe. Suppose this is a pipe we are having. This is a pipe, let us say. Okay. In this particular pipe, you are having a laminar flow taking place. Let me choose a centroidal axis. Suppose this over here is a centroidal axis we are having. Central axis. Suppose in this direction, which is my x-axis, and in this direction is my r-axis. Flow is taking place along x-axis. The first thing I'm supposed to talk about over here, which is the most important of all things, is the concept of velocity, the equation of velocity. So this entire page over here is dealing with the concept of velocity only. In this velocity, we are going to see three types of velocity. Please listen carefully. First velocity is known as your local velocity. Local velocity. Second velocity is known as your maximum local velocity. Third velocity is known as your average velocity. After seeing these three velocities, we are going to look at discharge. All those things we'll try and look in this particular page itself, this particular slide itself. So first thing first, the velocity profile in the case of laminar flow is supposed to be parabolic in nature. You're supposed to remember this thing. Don't worry, I'll mention that as a note. The velocity profile is supposed to be parabolic in nature. So let us say I take a particular section. I'm taking a particular section over here. This, let us say, the section. If I look at the velocity profile at this particular section, I'm supposed to have a parabola coming in. A parabola. One second. Let us say something like this. You're going to have a parabolic velocity profile. If I take any random radius small r, any random radius small r, that random radius small r is going to represent a velocity which is known as your local velocity u. And at the center, you see at the center, when r is equal to 0, the value of u is becoming your maximum, which is going to be your, let us say, u maximum. You're going to have u maximum. So first thing first, first note over here that velocity profile in laminar flow through pipes, laminar flow through pipes is, remember this thing, parabolic. It is going to be parabolic. Velocity profile is going to be parabolic. Now, what is that equation of velocity? So the first thing we are going to see now is the equation of local velocity. Equation of local velocity. Equation of local velocity. Please understand this thing. Your local velocity is varying with respect to which axis? The only axis u is varying with respect to is r. I told you yesterday that we are going to have two axes. One is r axis, the other is x axis. If you look at x axis, every section, if you see, every section is supposed to have same velocity profile. That means with respect to x, u will never vary. With respect to whom will u vary? U will only vary with respect to r. That is what you have to understand. So basically, when I write this particular velocity, you should observe that u has to be somehow a function of r. U has to be somehow a function of r. One more thing, this complete radius is represented by capital R. This complete radius is capital R. Now I'm going to write the equation of local velocity. The equation of local velocity goes something like this. The equation is u is equal to 1 by 4 mu. Mu is the viscosity of the fluid into minus dp upon dx multiplied to capital R square minus small r square, multiplied to capital R square minus small r square. So let me save it as some equation number 1. This equation you are supposed to memorize. U is equal to 1 by 4 mu minus dp by dx multiplied to capital R square minus small r square. Every term is clear to you. 1 by 4 mu is representing 1 by 4 times viscosity. Minus dp by dx, we have had a decent discussion regarding minus dp by dx previously. It is pressure gradient. It is supposed to be a positive constant value. Capital R over here is the maximum radius, that is the wall radius. and small r is the radius at which you are checking your local velocity. I hope it is clear to you. Furthermore, I can also talk about u maximum now. So second thing I'm going to speak about over here, second formula I'm going to speak about over here is maximum local velocity. Maximum local velocity. Now, what is this maximum local velocity? This maximum local velocity over here is u maximum. U maximum is basically u only, but at which value of r? At r equal to 0. It is u at r equal to 0. It is u at r equal to 0. ठीक है. If it is u at r equal to 0, then I can write over here the value of u maximum, maximum local velocity, has to be equal to how much? Put r equal to 0. You are going to get 1 by 4 mu minus dp upon dx multiplied to capital R square. This is a second equation. This is a second equation we are having. Now what I'm going to do is I'm going to get back to the equation of u. Let us get back to the equation of u. I see that the equation of u can also be written as 1 by 4 mu. Look at this equation. Look at this equation. 1 by 4 mu minus dp upon dx multiplied to r square multiplied to 1 minus r square upon capital R square. I can write like this also. Now please observe, what is this portion? This portion over here, 1 by 4 mu minus dp by dx multiplied to capital R square. This portion over here is u maximum. So from here I can imply u is equal to u maximum multiplied to 1 minus r square upon capital R square. U is equal to 1 minus, sorry, u maximum into 1 minus r square upon capital R square. Okay. So this is one more way of representing your local velocity. Now come to the third point. The third point over here. This third point is probably one of the most important points in this entire chapter. This is regarding the concept of average velocity of flow. It is average velocity of flow. Average velocity of flow. This average velocity of flow, what are you supposed to remember now? You see, this thing, if you don't remember, it is fine. If you remember this thing, it is sufficient. Likewise, after every name, I'll mention something that is more important than the equation coming next. For example, over here, I'm mentioning average velocity of flow, which is represented by V is equal to, it is equal to U max by 2. You have to remember this. Equation I'm going to write over here. Where my cursor is, I'm going to write the equation. But that equation is not as important as the relationship. अगर आपको relationship याद है, तब आप equation तो निकाल ही लेंगे. If you remember the relationship, you will eventually get the equation also. So what is the equation over here? Once I know U max, I have to divide it by 2. That is 1 by 8 mu minus dp upon dx multiplied to capital R square. So this happens to be my third equation over here. Okay. Third equation over here. Fourth point now. Final point, fourth point in this particular slide. It is regarding the concept of discharge. Discharge in laminar flow through pipes. This discharge, how should I think about discharge? I'm having these many velocities. Tell me which velocity is important for identifying the value of discharge. For identifying the value of discharge, average velocity is important. So I'll write over here, discharge has to be equal to complete cross section multiplied to average velocity. Now, complete cross section of a pipe is pi r square, is it not? Imagine I put a pi r square over here, multiply with velocity. I'm supposed to get the value of discharge is equal to pi by 8 mu into minus dp upon dx multiplied to r power 4. R power 4. So this is the fourth equation I'm having. Now what I want you to do is, I want you to write a site heading laminar flow through pipes. And I want you to mention whatever points I have highlighted over here, point 1, point 2, point 3, point 4, because when we are going to do problems, you'll require the formulas. That time you can look at the formulas straight away from your, what do you call it, book, rough book, or whatever you're using for writing. Chili, quickly take down the formulas, at least the formulas. Okay, three velocities: local, maximum local, average. And eventually after getting average, you're supposed to get discharge. Everything is having a logical sequence. Chronology is there. Understand the chronology. Okay. One more thing I'm mentioning. The value of alpha is supposed to be over here 2.0, and the value of beta is supposed to be equal to 1.333. That is 1.3 bar, 4 by 3. Okay. Chalo, quickly take this down. Bernoulli equation is applicable as long as the flow is steady, and you can, in this particular case, it is applicable because eventually you'll see we have the formula for head loss. Once we have the formula for head loss, then you can apply Bernoulli equation over here. Remember, whenever the flow becomes real, that time, if you know the value of head loss, then you can apply Bernoulli equation. I hope you have taken a snapshot and you have taken the formulas also. Okay. Now I'm moving further. This first slide was dealing with kinematic parameters. देखिए एक sequence है, very important sequence is there. All these parameters are dealing with kinematics of flow. For example, velocity, discharge, ये basic kinematics है. The next slide over here is going to discuss regarding the concept of losses. There are three things being lost. First thing being lost is pressure. Okay, so as you go forward, for example, this particular point is having some pressure P1. This particular point is having pressure P2. There is going to be a drop in pressure. The value of drop in pressure delta P has to be equal to how much? P1 minus P2. Okay, over here P1, over here P2. There is supposed to be drop in pressure. Okay, so next point we are going to discuss is regarding the loss. The first loss we are going to see is loss in pressure or drop in pressure. Eventually, by the virtue of drop in pressure, will the second point come, that is called as head loss. And because of head loss, you're going to lose some power. So you'll have power loss. So three things over here: pressure drop, then head loss, then power loss. Let us see now. So fifth formula. In the sequence of formulas, this is fifth formula. This is talking about pressure drop. Pressure drop. This pressure drop I'm going to represent with delta P. I'm going to represent with delta P. Now, the equation of pressure drop in the case of laminar flow is a very famous equation. Okay, this particular equation has one more name. It is called as Hagen-Poiseuille equation. Okay, I'm writing this thing over here. The equation of delta P in laminar flow. Laminar flow is also called as, what is it called as? It is called as Hagen-Poiseuille equation. This is one more name. Okay. What is the logic for getting the value of delta P? Logic is very simple. Remember the logic. The logic over here is wherever you see minus dP upon dx, replace it by delta P upon L. Wherever you see minus dP by dx, replace it by delta P by L. I'll give you a hint. Look at the previous slide. You are having the formula for average velocity. You have a rough book. Okay, feel free to scribble. Mention average velocity V is equal to 1 by 8 mu. delta p by L लिखिए, don't write minus dp by dx now, right? Delta p by L into r square. So v is equal to 1 by 8 mu delta p by L into r square. Please do that thing. And see what is the value of delta p you're going to get then. What is the value of delta p you're going to get then? So the value of delta p you're going to get will be equal to, check. Please do it. Don't try to listen to this thing just like a movie. No, you do some things now. Okay. Otherwise you'll feel bored because these things are only some formulas and then problems. 8 mu VL, 8 mu VL upon R square. You are supposed to get this value. 8 mu VL upon R square. This is the value of delta P, which is also equal to, if you want to write in terms of diameter square, this happens to be 32 mu VL by D square. 32 mu VL by D square. Similarly, I want you to develop the equation of delta P by using discharge. कैसे करेंगे आप? You'll first start with Q is equal to pi by 8 mu delta P by L into R power 4. Do that thing. Pi by 8 mu delta P by L into R power 4. From there, get the value of delta P. Get the value of delta P. Delta P now has to be 8 mu QL upon pi R power 4. Okay. If you want in terms of diameter, you can say R is basically D by 2. So you're going to get 128 mu QL upon pi D power 4. These two are forming my equation number 5. These two are forming my equation number 5. Next equation I'm going to have over here. Next equation, let us say sixth equation over here, is the equation of head loss. It is the equation of head loss. Okay. How to get the equation of head loss? Head loss you can get by that particular formula. Yesterday I discussed with you that head loss is equal to delta P by gamma. If head loss is delta P by gamma, then you can write over here the formula for head loss. The formula for head loss. If we are preferring diameter, okay, generally we prefer formulas in terms of diameter for pressure drop and head loss. If we are preferring diameter, then I'm supposed to write over here 32 mu into VL upon gamma times D square, also equal to 128 mu into QL upon pi times gamma times D power 4. This is the value of head loss I'm having. Let me save it as some equation 6. I'm saving this as equation 6. Okay, fine. I have got the value of head loss. Now, by the virtue of head loss, you are going to have something known as power loss. Power loss. There's going to be some power loss induced because of head loss. This value of power loss, okay, this is capital P with an L over here that is representing power that has been lost, has to be equal to. अब इसके लिए कहाँ पे जाएंगे आप? Where will you go for getting this particular formula? To get this particular formula, you're going to go back in Bernoulli equation class. We have discussed the concept of power. We said power is equal to gamma into Q into that particular head, which is corresponding to power. The head corresponding over here is head loss. Since I want power loss, I'm using head loss over here. अब देखिए, never use this head loss over here because he is talking about velocity, whereas you are having discharge over here. Prefer this head loss. This head loss you prefer. If you put in this head loss over here, then gamma cancel off, Q becomes squared up. Therefore, the value of power loss has to be now equal to how much? The value of power loss has to be equal to 128 mu into Q square times L upon Q square times L upon pi times D power 4. This will be the value. Let me take this equation as equation 7. As a matter of fact, this power loss has one more form. Now you see over here, head loss was equal to delta P by gamma. You cancel gamma and gamma over here, you're going to get delta P into Q. Therefore, the value of power loss has to be also equal to how much? It also has to be equal to delta P into Q. That is the pressure drop multiplied to Q. This has to be the this has to be one more formula for power loss. Okay, I'm again getting it from here itself. I'm not highlighting it much. One more thing. In this particular slide, what is more important? You're supposed to remember this thing. I have discussed this thing already. In the morning also I've discussed this thing. This is important and this is important. I told you whatever I'm writing beside is important. So let us say this is beside over here, this is beside over here, this is beside over here. Eventually formulas anyone can get. Relationship yaad hona chahiye. You are supposed to remember the relationship. Please take down the formulas quickly in your notes. The first slide for today's class is this thing. I have discussed the fundamentals of internal flow again in the morning class before starting. Those will be important. So I've discussed them over here. This is the first slide. Then the second slide was laminar flow and so on. Okay. See, if you come late, no problem. You'll be getting PDF any which way. So don't worry about that. This is the third slide for today's class. And the final slide over here. That is why, Yash, that is correct. That is the reason why I have discussed fundamental relationships previously. Those relationships are very important. If you know those relationships, you can anytime get any formula. I'm telling you, over here, you'll be seeing a lot of formulas. But even I sometimes feel I don't remember all these formulas. I try to get the formulas on the spot, and it does not take more than 15-20 seconds to get any formula. Okay. On the spot, I get formulas. It does not take a lot of time. Velocity in pipe does not vary with respect to x because the pipe's diameter is constant. Continuity equation says area is same, velocity should be same. Chaliye, this is regarding the losses. Okay, you see now the slides also I'm giving you in a particular way that they are having a particular commonality over here. You see in this particular slide, everything was dealing more with kinematic parameters. In this particular slide, you are dealing mostly with losses. You see pressure is being lost, head is being lost, power is being lost. Now, the last slide over here, the last slide is regarding friction slide. This is friction slide. Over here, kitne ho gaye? 7, 8th one now. 8th one. I'm going to start with Fanning's coefficient of friction. Fanning's coefficient of friction. Fanning's coefficient of friction. I would ask you to straight away remember the formula. This is represented by F prime. I would ask you to straight away remember the formula. The formula for Fanning's coefficient of friction, F prime, is equal to 16 upon Reynolds number. In laminar flow, it is 16 upon Reynolds number. Next thing is Darcy friction factor. Darcy friction factor. This Darcy friction factor is represented by F. It is equal to 4 times F prime. Therefore, the value of F has to be 4 times this thing is going to give you 64 by Reynolds number. Final formula is something which you have seen already. Final formula you have, excuse me. Final formula you have seen already. This formula is shear stress formula. Shear stress formula. The formula for shear stress we have discussed already. The value of tau has to be equal to minus dp upon dx multiplied to r by 2. Multiplied to r by 2. So let us say this is some equation 8 I'm having. This is some equation 9 I'm having. This is some equation 10 I'm having. These are the equations I'm having over here. And now I'm going to mention a note. This note also you have seen in yesterday's class. The note is all these formulas are valid for pipe in what orientation? Horizontal orientation. If the pipe is inclined, then what am I supposed to do? Wherever in these formulas you are seeing pressure, remove pressure, replace it by piezometric pressure. Yesterday also I mentioned, again I'm going to write this note. Very important note. Till the time I write this note, you take down these formulas. All the above formulas are valid for horizontal pipes. Horizontal pipe. If pipe is not horizontal, pipe is non-horizontal, replace pressure by piezometric pressure. Replace pressure by piezometric pressure. Okay. Wherever you see pressure in that particular formula, replace the pressure term by piezometric pressure. You can take a snapshot of this particular slide. Then we will start with questions. So these are the notes for your laminar flow through pipes. Nothing much is there. No theory is there. Straight away formulas. I have discussed all the formulas. I told you how to remember also these formulas. Okay. Divide the formulas into 3 sets. First set is kinematic set. Second set over here is a losses set. Third set over here is the concept of friction. You see, everything is dealing with friction. Shear stress is like friction only. Fanning's coefficient of friction, Darcy friction factor, everything is dealing with friction. Now I'm going to start with the problems. Yes, sir, this is very important for GATE examination. Okay, chaliye. Now we have to take down some problems. I am going to open your literature, probably around page 71, 72 or 73, somewhere around that. You'll be finding questions on laminar flow. Okay, questions on laminar flow. Please see questions on laminar flow. Questions on laminar flow. This is in the book itself, that question is there, which is GATE 2-mark question. 2 marks question, civil engineering paper. Okay. There is a particular pipe which is inclined, some 10 centimeter diameter, 10 mm diameter pipe or something. You see that page 76 for some people, 72 for some people. Tell me which question number is there. A pipe is inclined, a 10 mm diameter pipe, inclined at an angle 30 degrees. Last question, around last question it is. Please mention which question is it. Question number 10. Okay. So in that particular page, this is question number 10. This is question number 10. On this question, I'm going to ask you, first of all, whatever is there that we will discuss. After that, I'm going to ask you one more extra question. Chali. Please read the question for yourself once. Read the question for yourself once. Question number 10 from your literature. This is a 2-mark civil engineering question. Okay, it is fill in the blank kind of question. Read the question for yourself once and draw a rough diagram till that particular time. Read the question and draw a rough diagram. Page number 72, 73, 74, 75, 76. Check. Sorry. Now I'm going to discuss the question. The question says you're having a pipe which is inclined. I'm going to mention all the data. Let us say you have a pipe which is inclined, something like this. There's a particular pipe. But when you're drawing in examination, let me tell you, when you're drawing in examination, you are not going to draw this kind of diagram. Whenever you draw in examination, never draw this kind of diagram for pipe. Always draw a line diagram. This will take a lot of time, lot of effort. Better than this, whenever you're drawing in examination, 1 second please, always go for line diagram. What do I mean by line diagram? Line diagram basically means just show the pipe like this. That's it. This is a pipe. Okay. This is not representing a line. It is representing a complete pipe. Inside portion hollow, flow is taking place over here. Then he goes on to say that in this particular pipe, the flow is taking place in upward direction. If you have read the question, he has mentioned the flow is taking place in upward direction. This, let us say, some section 1. The flow is taking place till here. This, let us say, section 2. The length of the pipe is equal to some 10 meters. 10 meters. Furthermore, he goes on to say that the angle of inclination over here, is equal to, 1 second. The angle of inclination over here is equal to 30 degrees. This angle over here is equal to 30 degrees. Okay, angle is equal to 30 degrees, fine. He says the diameter of the pipe is equal to 10 mm. So convert everything in SI units so that you don't have a problem later on. Diameter is equal to 10 mm. The fluid flowing over here is having a viscosity, viscosity, I don't remember, density, something. Someone please mention viscosity and density. Okay. He said the value of G you can take is equal to 10 meters per second square. Someone please look into the book and tell me the value of mu and viscosity, mu and density. The value of G is equal to 10 meters per second square. He has also given you the value of velocity. Velocity also is given to you. All these values are given to you. Velocity also, someone please tell me. Viscosity is 0.1 Pascal second. 0.1 Pascal second. Density is 800 kg per meter cube. And velocity over here, I think, is equal to 0.1 meters per second square. 0.1 meters per second square. 0.1 meters per second, sorry, not second square, 0.1 meters per second. All these things are given to you. The question asked over here is find the drop in pressure. The question is find drop in pressure. Flow taking place upward, find the drop in pressure. Now listen to me. This is a previous GATE examination question. Similar kind of question can appear again, and it is a good question for examination. Okay, not a difficult one, not an easy one also. but a reasonable question in examination. Whenever these kind of questions come, first thing, mark my words over here, first thing, always find out the value of datum difference first of all. It will be very helpful for you. Datum difference. Okay. What is the meaning of datum difference? Let us say, if I look over here, this distance over here is representing my datum difference. This is representing my datum difference. And this is equal to Z2 minus Z1 equal to how much? Now, 10 sine 30. Everyone knows 10 sine 30. That is equal to how much? 5 meters. This will be very helpful for you. Datum difference, we know now. Okay. Chaliye. Now we have to find out the drop in pressure. Now you might think, ठीक है, drop in pressure. We have a formula for drop in pressure. Delta P is equal to 32 mu VL by D square. If you're thinking that straight away you're going to use this formula, you have made two mistakes. Not one, two mistakes. If you're thinking for this particular problem, straight away you're going to use this particular formula, then you have done two mistakes. Let me tell you what mistakes you have done. First mistake, that formula is not valid now for delta P. That formula is valid for delta P star. Kyun? Why is it valid for delta P star? You are having a non-horizontal pipe. Pehla mistake ye hua. Second mistake is even more fundamental mistake. That formula is for laminar flow through pipes. In the question, did he mention anywhere that the flow is laminar? No, he did not mention the flow is laminar. That means whenever you are in examination, don't make your own assumptions straight away. First check whether the flow is laminar or not. Today you know you are studying laminar flow chapter. That is why you know this is laminar flow. Okay, today it is fine. But in examination, you do not know whether it is laminar flow or not. So first check whether it is laminar flow. So whenever these kind of questions are given to you, always start the solution with finding out the Reynolds number. It will be helpful. Okay. The Reynolds number value, RE, we know is equal to, chaliye, please do with me very quickly, rho VD by mu. First thing I'm going for Reynolds number, rho VD by mu. Okay, you don't need calculator for these numbers, very simple numbers. Velocity is equal to 0.1, diameter is 0.01, mu is equal to 0.1. 0.1 and 0.1 cancel off. 0.01 consumes of two zeros from here. That means the value of Reynolds number you are going to get is equal to 8. This is, let us say, equation 1. Reynolds number is equal to 8. Okay. Check. You must be getting the same value of Reynolds number. Please be quick. Datum difference is basically trigonometry. You complete the triangle, you find the height over here. That height is equal to final height minus initial height, Z2 minus Z1. That is datum difference. After getting Reynolds number, we are confirmed that this is laminar flow. Now let us apply the formula. Which formula? Delta P nahi likhenge aap. You will not write delta P. You will write delta P star. That formula is for delta P star. What is the formula? 32 mu VL upon D square. This is a formula. If you don't remember, never mind. I do not stress much on remembering these formulas. Okay. If you know one or two formulas, anyone can get these formulas very easily. So this is delta P star. Put in the numbers now. 32 ho gaya yahan pe. Mu ki value has 0.1. Velocity is again 0.1. Length is equal to 10 divided by D square is equal to 0.01 whole square. Okay, square bhi aana hai. Check the value of delta P star. Check the value of delta P star. You are supposed to get 32 followed by 3 zeros. Very simple numbers. You see, these two will take off 1 power from here. He will become 100. Then 10 multiplied 1000. 1000 into 32, 32,000 Pascal. Or you can say it is equal to 32 kilopascal. Save it as some equation number 2. अभी ये आंसर नहीं है. He wants drop in pressure. He wants drop in pressure. Please be quick. I hope you have finished here. He wants drop in pressure. Now I'll say delta P star is basically equal to P1 star minus P2 star. अच्छा ठीक है. Which is equal to P1 plus rho g Z1 minus P2 plus rho g Z2. This is the value of delta P star. Delta P star. Okay, fine. I want over here drop in pressure. That means P1 minus P2 I want. Keep P1 minus P2 on one side. Keep P1 minus P2 on one side. It has to be equal to how much? Delta P star. Now P1 minus P2 is delta P star. This will go over here. This will go over here. When he goes over here, he becomes minus. When he goes over here, he becomes plus. So it is going to be plus rho g Z2 minus rho g Z1. So this is delta P star plus rho g into Z2 minus Z1. देखिए datum difference कहाँ पे काम आया. Look over here how datum difference has been helpful for you. You see Z2 minus Z1, you know, is equal to 5 meters. Directly put in the numbers, which implies P1 minus P2 is equal to delta P star is 32,000 plus rho is equal to 800, G is equal to 10, Z2 minus Z1 is equal to 5. If you put in the numbers, you're supposed to get over here 72,000 Pascal, or you can say 72 kilopascal. This is supposed to be your answer. Please check. Please check this thing. All of you should be getting this answer. Please be quick. Now I'm going for an alternative approach. There is an alternative approach to this kind of problems. Okay. Yes, very good, Mohit. That is what I'm going to discuss now. You can take datum line anywhere, but datum difference, if you take anywhere the datum line, datum difference will still be equal to 5 meters only. Okay, don't worry. If you take datum line anywhere, let us say at the G level I'm taking, where I wrote G now, that level I'm taking datum line, still the datum difference will be equal to 5 meters. Now a suggestion is given by Mohit. That is a good suggestion. That is what I'm going to use now. It is an alternative method. If I am attempting this question in examination, I will prefer alternative method. That is more favorable for me. I have created a duplicate slide. In 6F also I'm having same thing. 7F also I'm having same thing. Over here, I'm going to see what is the alternative approach. You see, whenever you have the value of Reynolds number in laminar flow, it is better to find out head loss by finding friction factor. Once you get head loss, you can use Bernoulli equation. देखिए, please understand this thing. Okay, come out of that frame of mind of examination and think logically. Problem with Bernoulli continuity equation every time you apply. The problem with Bernoulli equation is the moment the flow becomes real, Bernoulli equation becomes difficult to apply. Listen carefully. The moment flow becomes real, Bernoulli equation becomes difficult to apply. Why? Because Bernoulli equation in real flow demands one extra term called as head loss. As long as you don't know the value of head loss, applying Bernoulli equation becomes difficult. But if you know the value of head loss, then Bernoulli equation is easy. That is what we are doing now. We know that Reynolds number is equal to 8. Now this implies the value of friction factor. The value of friction factor is equal to 64 by Reynolds number. That is equal to how much? 64 divided by Re is going to be 8. Okay, friction factor is known. Now I will write the formula for head loss. Head loss is equal to how much? FLV square upon 2GD. चलिए करिए मेरे साथ फिर से. Do along with me again. Okay, put in the numbers. F is equal to how much? 8. L is equal to how much? 10. V is equal to 0.1 square by 2 times G is 10, D is 0.01. How simple numbers they have asked in GATE. These two get cancelled off, these two get cancelled off, these two will yield only 4. So I see the value of head loss over here is equal to 4 meters of fluid. 4 meters of fluid. Save it as some equation 2. Now the moment I get head loss, my Bernoulli equation is very strong now. I will apply Bernoulli equation. I have over here P1 by gamma plus V1 square by 2G plus Z1 has to be equal to P2 by gamma plus V2 square by 2G plus Z2. Not to forget the most important term over here, head loss. Okay. By continuity equation, I know that this value and this value are supposed to be same. Velocity is same, cancel off velocity. I want the value of P1 minus P2. Na? I want the value of P1 minus P2. So let us say P1 minus P2 whole by gamma is equal to how much? It is equal to Z2 minus Z1 plus head loss. If I take Z1 over here, I have Z2 minus Z1, not to forget head loss. This implies P1 minus P2 has to be equal to gamma times Z2 minus Z1 plus head loss. So this is equal to, implies P1 minus P2 is equal to, gamma is equal to how much over here? Density 800 है, G से multiply कीजिए, so gamma is 8000. Z2 minus Z1, we know it is equal to 5. Head loss over here is equal to 4. Value should give you the same answer, 72,000 Pascal equal to 72 kilopascal. This is supposed to be the value. Both the formats, you are supposed to get the same answer. Yes, this is in volume 1. This is in volume 1. I take questions only from volume 1. Volume 2 is for your practice. Velocities are getting cancelled because of continuity equation. The cross section is same, the velocities will be same. Okay. Someone has asked me that generally we do not consider the value of head loss in the equation. See, when to neglect head loss, when to consider head loss. You are supposed to neglect head losses whenever you are having an indication towards ideal flow or nothing is indicating towards losses. That time neglect head loss. But in these questions, the moment viscosity is mentioned to you, tell me the flow has become real. He is expecting you to use head loss over here. Use head loss over here. Now I am going to ask you some questions. My question over here. I'm taking the next slide to discuss the question. Okay. The question goes something like this. It says, find the rate of shear strain. Rate of shear strain at a distance of 3 mm from the wall of the pipe in the above question. Okay. Find the rate of shear strain at a distance of 3 mm from the wall of the pipe in the above question. This question itself is worth 2 marks in examination. Okay. Again, easy only. It is not that much difficult. Everything is formula based. Everything is formula based. Actually, find the rate of shear strain. पहली बात तो rate of shear strain किसे कहेंगे आप? What is the meaning of rate of shear strain? Rate of shear strain means du upon dy. This is called as your rate of shear strain. Rate of shear strain is du by dy. Arey yaar, this voice problem. Is the audibility is it audible now? Okay, fine. Okay. Chaliye. Now let us start this question. Let us start this question. I hope you have taken down the till here. Find the rate of shear strain at a distance of 3 mm from the wall of the pipe. Now, rate of shear strain basically means du by dy. Du by dy, that is rate of shear strain. How to get the idea of rate of shear strain? Rate of shear strain you should get from shear stress. Look over here. Theory dekhiye aap. Look at this particular point. Shear stress can be obtained by Newton's law of viscosity. Padhe the ye point. We have discussed this point. If shear stress can be obtained by Newton's law of viscosity, then I can write tau is equal to, Newton's law of viscosity says what? Mu into du upon dy. Also tau is equal to minus dp upon dx multiplied to r by 2. Correct? If you say correct, then you are wrong. This is wrong now. You should write minus dp star by dx multiplied to r by 2. Are you following this? Are you following this thing? Is it fine? Is it fine? Minus dp by dx nahi likhenge aap. You won't write minus dp by dx. Why won't you write minus dp by dx? You are having a non horizontal pipe. You are supposed to write minus dp star by dx over here multiplied to r by 2. This is what you are supposed to have. This implies the value of du upon dy is equal to how much? It is equal to 1 by mu into. Now, can I write minus dp star by dx as delta p star divided by L multiplied to r by 2, multiplied to r by 2, r by 2. This is the value I'm going to use. Now, don't memorize this as a formula. If you keep memorizing many things, I'm telling you, guarantee you'll forget those things only. Whatever you stress on memorizing, that only you'll forget. That is human nature. Okay. Try to obtain things and forget also. Okay. You should be in a position to forget things also. That is very important because you are not writing only one subject in examination. You're writing multiple subjects. इसीलिए obtain things. Once you get this question is finished. इसको भूल भी जाओ आप. ठीक है? When again you will see this question, again obtain this thing. These are not that much important formulas. These can be obtained very quickly. Now, he said 3 mm from the wall of the pipe. 3 mm from the wall of the pipe. देखिए, imagine this is center line. This is center line. This is wall of pipe. Wall of pipe. We know that this distance is equal to what? Capital R. From center line till wall of pipe is capital R. He wants this, he gave this distance. Whenever you measure distance from wall, that is represented by y. He said y is equal to 3 mm. He said y is equal to 3 mm. But I want r in this thing. What is the value of small r? Small r, if you see mathematics, basic mathematics, it is equal to capital R minus y. Capital R minus y. So now I can do that. I can say that this implies the value of du upon dy is equal to 1 by mu delta p star divided by L multiplied to capital R minus y. In place of small r, I'm writing capital R minus y divided by 2. Chaliye. Now you have everything ready with you over here. Over here, you have everything ready with you. Put in the numbers now. Mu is equal to 0.1. Delta P star sometime back you have found out. If you did not find out, then you have to find out over here. Chaliye, delta P star, I know already, it is 32,000. So 32,000 divided by. Length of pipe was 10 meters. Capital R over here is 0.005. Diameter was 0.01. Capital R is 0.005. Y over here is equal to 3 mm. That is 0.003 divided by 2. Put in the numbers, get me the answer for this value. You are supposed to get over here 32 second inverse. This is the value of du upon dy. 32 second inverse is the value. Please check. Yes, how star is coming, how delta P star is coming. The reason for delta P star to come is this note over here. This note is very, very important. All the formulas are valid for horizontal pipe. If the pipe is non-horizontal, replace pressure by piezometric pressure. So pressure था यहाँ पे, piezometric pressure कर दिया उसको आप. Okay. You see again, few days back, someone asked me that there is difficulty in units. From that day onwards, every time I'm writing units in SI only, answer also I'll get in SI units. That is the best way in examination. Okay. Best way in examination is to write SI units always. Chaliye, I hope this is finished. Why are we not putting Y directly? Because we want R. Over here, this formula is from center. R over here. You can't put Y. Y is measured from wall. The distance is from center to be taken, right? That is why we are looking at this thing. I hope this is clear to all of you. Now, two questions whose answer it is better if you can remember. Two questions whose answer it is better if you can remember. Question number 1. These can be coming directly in some examinations, not gate, but okay. Question number 1 over here. The least value of friction factor in LF means laminar flow through pipes is the least value of friction factor in laminar flow through pipes is. Chaliye, quickly find this answer. Two questions I have mentioned over here. Question number 1, I'm solving. Let me check if anyone got the answer. Very good, very good. Many of you have got the answer. Very good. What is the formula for friction factor 64 by RE? यश प्लीज चेक कितने जीरो लिख दिया आप. चलिए, what is the formula for friction factor 64 by RE? If I want minimum of F, I want maximum of RE. Simple logic. Inverse variation है. Inverse variation में for one thing to become minimum, the inverse quantity should become maximum. What is the maximum value of Reynolds number in laminar flow? 2000 is the standard value we are taking according to Indian books. Okay, if you are referring to foreign authors, they'll take 2300, but don't do that thing. In foreign authors, they'll say 2300, but don't take this value. If anyone is referring, please don't take that value, because you are writing examinations in India. So as long as you're referring to Indian books, you're going to get the answer for examinations in India. So it is going to be 2000. Fine. So this is equal to 64 divided by 2000. You are supposed to get 0.032 as the answer. This is the least value of friction factor in laminar flow through pipes. I hope all of you are getting this value. Second question. कौन ट्राई किए? सेकंड क्वेश्चन कोई ट्राई नहीं किए? The local velocity is equal to average velocity in laminar flow through pipes when R is equal to how much R? Small r is equal to how many times capital R, he's asking. नहीं. Yes, Roshan Shibin Shahid, correct answer. Now R is equal to how many times smaller? Now local, he's saying local velocity is equal to average velocity. Local velocity U hai, average velocity V. Ab local velocity was equal to U maximum multiplied to 1 minus R square upon capital R square. This was local velocity. Average velocity was equal to U maximum divided by 2. अब आप U maximum cancel कर दीजिए. Cancel of these two things. Now you develop the relationship of small r in terms of capital R. So what are you going to get? 1 minus small r square upon capital R square is equal to half, which implies small r square upon capital R square is equal to half, which implies small r is equal to capital R by root 2. Small r is equal to capital R by root 2. From here, you are going to get small r is supposed to be equal to 0.707 capital R. This is supposed to be your value. This is supposed to be your answer. Okay. This is for which flow? This is for laminar flow. This is for laminar flow. Since this number is quite easy to remember, I will give you one more number. Okay. One more number that is for turbulent flow. If you can remember. If you don't remember, then also it is fine. Okay. That number is also easy to remember. If same question is asked, removing laminar flow, he's saying turbulent flow. Same question, पूरा wording same है, सिर्फ laminar निकाल दिया, turbulent लिख दिया. Then what should the answer be? The answer in this case should be, you are having 707 ना, उसको आप कर दीजिए 777 capital. This is going to be the answer in the case of, we did not discuss turbulent flow, but still I'm giving you the answer now because you see easy है याद रखना यहाँ से. 0.707 in laminar, 0.777 in turbulent. Those who are preparing for IES better remember. All these three answers better remember, those who are preparing for IES. Okay. Chaliye. This was regarding the concept of laminar flow through pipes. Now moving further, I'm going to discuss the concept of laminar flow between fixed parallel flat plates. Next topic I'm discussing over here is laminar flow between fixed parallel flat plates. Laminar flow between fixed parallel flat plates. Let us see.
Okay, this is that was 3 star I mentioned importance wise. Its importance is one step lesser than the pipe problem. This is one step lesser. Okay, one moment please. Let me draw a diagram. Imagine you are having two plates which are parallel to each other. I hope they are looking parallel to each other. Two plates parallel to each other. Suppose both the plates are fixed. Both the plates are fixed plates. Both the plates are fixed plates. Okay. There is some flow taking place in this particular direction. Flow is taking place in this direction. First thing I'm going to look at is the concept of velocity profile. The concept of velocity profile. The velocity profile over here is again going to be parabolic in nature. It is going to be parabolic in nature. Very good diagram. So you're having a parabolic velocity profile. Then I'm going to look at the shear stress profile. Shear stress profile is going to be linear in nature. Equations will write, don't worry. Shear stress profile is linear in nature. It is going to be linear in nature, something like this. Chaliye. One second. Center line, let us say is center line over here. This, let us say, is a center line. Once again. Now there are two axes important for us. One axis over here is this particular axis, which is x-axis. The other axis is the axis which is emerging from the wall of the pipe. This is y-axis. One axis is x, the other axis is emerging from the wall of the pipe. That is y-axis. Okay. The local velocity is represented by this. Let us say this is some random local velocity. And this velocity over here is your u maximum, maximum local velocity. Okay. This shear stress is some random shear stress. This is some random shear stress. And this shear stress, which is at the boundary, it is your wall shear stress, tau naught. Wall shear stress, tau naught. Okay. So over here, let me mention velocity profile. Velocity, let me write full form. Velocity profile, and you're having shear stress profile. Shear stress profile. After discussing this, I'm going to give you a 2-mark question from here. Okay, 2-mark question from here. So please look at the formulas, very simple formulas. Again, just by knowing one formula, every other formula you will find out eventually. Okay, sequence samajhna hai, chronology you have to understand. Okay, velocity profile is going to be parabolic in nature. Velocity profile is parabolic in nature. Shear stress profile is linear in nature. Linear in nature. This is what we are having. Up we are going to look at the formulas. First formula, local velocity. Formula number one, you're going to have is local velocity. Always local velocity will be important formula. Okay. Wahan se everything you can develop. Once you know local velocity, you can develop everything. This local velocity over here is u. And this time u should be a function of which axis? Remember, u can never be a function of x-axis. U can never be a function of x-axis because according to steady nature, every section will have same value of velocity. So u is a function only of y-axis. U is a function of y-axis. Acha, one more thing I have missed mentioning. That is the distance over here is capital B. This distance is capital B. So capital B over here is width between the plates. The width between the plates is capital B. Actually, u is a function of y-axis. The formula for u is equal to 1 by 2 mu minus dp upon dx multiplied to b times y minus y square. B times y minus y square. This is the first equation. You have to memorize this equation. No escape. You have to memorize this equation. Rest of the things are extremely easy. Very, very easy. Second thing. Maximum local velocity. Maximum local velocity. Now you only tell me maximum local velocity ke liye you are going to say u maximum is basically u only, but at the value of y equal to how much? At what value of y? Dekhiye, y is measured not from center, y is measured from the wall. That means at y equal to exactly b by 2, you are supposed to get maximum local velocity. You are supposed to get maximum local velocity. You can take y from upper plate also. Very good. You can take y from Ajit. Very good. You can take y from upper plate. Never mind. That is also correct. Okay. So the value of u maximum, please write along with me. U maximum will be equal to. Ab dekhiye, I'm straight away writing this. Please read this as b into b by 2 minus b by 2 whole square. That is b square by 2 minus b square by 4. B square by 2 minus b square by 4 is b square by 4. Take that 4 over here. Check, you should get 1 by 8 mu minus dp upon dx multiplied to b square. Multiplied to b square. Third thing is a question you are going to type the answer. Average velocity. Average velocity. Average velocity. The value of average velocity is equal to something times u maximum. वो something क्या है आप टाइप कीजिए. I want to see how many of you remember. Very good, very good. Shankar, Shiva Ganesh. Very good. Jahangir Ansari, Swarangi. You all remember that something over here is 2 by 3. मैं आपको बोला था, I told you when discussing in kinematics, I had taken this particular problem. Okay. I replaced this entire thing 1 by 2 mu into minus dp by dx with a c because all these things are constant. I replaced it with c. I said local velocity is equal to c into b times y minus y square. Find the value of discharge, find the value of maximum local velocity, find the ratio of u maximum to v. All those things I discussed. So this was the value. अगर आप ये put करेंगे, if you put this value, the value of v becomes equal to 1 by 12 mu minus dp upon dx multiplied to b square. Finally, I'm going to talk about, in this particular slide, I'm going to talk about discharge. Discharge. Discharge over here is Q. Discharge over here is Q. Q is equal to area times velocity. Let us say there is some width perpendicular to screen. W is width perpendicular to screen. जब आप प्रिंट आउट निकालेंगे डीडी टेस्ट पेपर, width perpendicular to paper वो टाइम पे. Okay. So discharge will be equal to how much? Area कितना है अब? B है and screen से ऊपर कितना distance आ रहा है? W आ रहा है. So you're having area B times W. So multiply B times W. You're supposed to get discharge is equal to how much? It is equal to 1 by 12 mu minus dP upon dx multiplied to B cube times W. This was my equation number 2. This is my equation number 3. This is my equation number 4. Quickly take down the equations. Now you see how much simple it is. ये याद रखना है आपको, ये याद रखना है आपको, ये याद रखना है आपको. This, if you want to forget also, you can't forget. Okay, Q is equal to AV. If you want to forget, still you can't forget that thing. चलिए quickly take down. V is 2/3 of Umax. I have done that particular problem in kinematics. Please refer to that kinematics chapter's questions. You will be understanding. Okay. Chaliye, I hope you have taken down all the formulas till here. Now you see again, this particular slide I have discussed is having which formulas? It is having all the formulas corresponding to your kinematic parameters. Kinematic parameters formulas you are having. Okay, next slide, I'm going to discuss losses along with shear stress. Everything will be closed in this particular topic in next slide. So over here, we'll talk about the losses now. First thing I'm going to discuss over here is pressure drop. I'm going to discuss regarding the concept of pressure drop. So fifth formula, I'm having pressure drop. This pressure drop is represented by delta P. And what is the logic for getting delta P? Very simple logic. Wherever you see minus dP by dx, replace it by delta P by L. I told you this thing. So in the previous slides, you are having the formula for velocity and discharge. Velocity and discharge का formula था आपके पास. वहां पे what you do now? You replace minus dP by dx with delta P by L and get the value of pressure drop. So what are you going to get then? Do it yourself. Check, you are supposed to get the equation as 12 mu VL upon B square or 12 mu QL upon B cube into W. This is the equation you are supposed to get for pressure drop. Okay, fine. Now coming to sixth formula. Sixth formula, head loss formula. Head loss formula. The formula for head loss, very simple. I'm going to say head loss is equal to delta P divided by gamma. Head loss is delta P divided by gamma. Therefore, the value of head loss is now supposed to be equal to how much? Head loss value is supposed to be equal to this divided by gamma. So you're either going to have 12 mu VL upon gamma into B square, or it is going to be equal to 12 mu QL upon gamma into B cube into W. This is a formula for head loss. This is a formula for head loss. Power loss also you can find out. I'm not stressing on power loss over here, not that much important. Last formula that I'm going to mention over here is the formula for shear stress. It is a formula for shear stress. What are we going to do to develop the equation of shear stress? Okay, this is going back to Newton's law of viscosity. Tau you say is equal to mu into du upon dy. You'll get the value of shear stress. You say tau is equal to mu into du upon dy. you should get the value of shear stress from there. So basically tau now becomes equal to mu into d upon dy of what was velocity? Velocity was 1 by 2 mu minus dp upon dx into b times y minus y square. This was the equation. So ultimately, I'm going to get the equation of tau is equal to. These things are constant. You differentiate this, mu and mu cancel off. So you're going to have minus dp upon dx multiplied to b minus 2y whole divided by 2. This is the equation of shear stress. Let me take it as some equation 7. Equation 7. Finally, I'm having 8th equation, last equation over here, wall shear stress. Wall shear stress. Final equation is wall shear stress equation. Now, what is wall shear stress going to be? Very simple. Wall shear stress is shear stress at y is equal to b upon 2. At y is equal to b upon 2, you are supposed to get wall shear stress. So put b upon 2 over here. Sorry, y is equal to 0, not b upon 2. 1 second. Y equal to 0 you put y equal to 0 for wall. Y is equal to 0, is it not? Put y equal to 0, then the value of tau naught becomes minus dp upon dx multiplied to b times y. This is the formula for wall shear stress. Quickly take down these equations. Just take down these equations, okay? Don't write all the stories. Just take down the equations. Okay, I hope you have taken down all these things. Yeah, you can imagine per unit width and neglect W also. Yeah, better write all these formulas in short notes. But even though it is very easy to remember these things, you see, still you will find it is easy to remember all the formulas. You see over here, just by remembering this one formula, you can develop these 3 formulas. These formulas also you can develop. Only shear stress is there. That is also not difficult. You're going to Newton's law of viscosity. You can take the formula for average velocity for finding power loss. There is nothing wrong with that. Only thing is you will get velocity and discharge both in the equation. Nothing wrong. This is the slide for the first slide for laminar flow between fixed parallel flat plates. And this is the second slide. Now let us take third slide question we'll take. That question is a very, very good question. I am picking up that question from Dr. A.K. Jain's book. Okay, very good question. Worth 2 marks in your examination. Dr. A.K. Jain is one of the best books in India for competitive examination. According to me, the most balanced book for competitive examination is Dr. A.K. Jain. It does not oversimplify the subject. It does not make the subject very difficult to read also. And it gives you every kind of problem starting from PSC level to IS level, and readable book, not as bulky as Modi and Sit. Most balanced book. Chaliye. Look over here. The question goes something like this. Dr. A.K. Jain, the book's name is Dr. A.K. I have mentioned this book in the first class itself. Look over here. The question says, there is a tank. Suppose there is a tank. 1 second. Let me finish it, then you'll understand where the tank is. One moment, please. Okay, now this is a tank. Let us say the tank is having some wall thickness over here. I have shown the wall thickness. The diagram is, one moment please. Suppose this is a wall of the tank. Fine. Inside this tank, you are having some fluid. Let us say there is some fluid inside this tank. There is some fluid present over here. Some fluid is present over here. The question says, at some depth, the depth I'll mention to you, at some depth below from the interface, somewhere over here, a crack is developed. A horizontal crack is developed. Okay. That crack developed over here is having some thickness. Let us say the depth over here is equal to 2 meters. At a 2 meters depth, the density of the fluid is equal to, let us say, 1200 kg per meter cube. The viscosity is equal to, let us say, 12 poise. 12 poise. A crack is developed. Okay. The height of the crack, is equal to some 4 mm. Height of the crack is equal to some 4 mm. Fine. The length of the width of the wall is having a width of 10 centimeters. The wall is having a width of 10 centimeters. The question asked over here is, find the discharge per unit width perpendicular to the screen through the crack. Find the discharge per unit width perpendicular to the screen through the crack. So how much discharge? You see, from this crack, there has to be some seepage taking place. Some flow is supposed to take place from this particular crack. You are supposed to identify how much is the discharge taking place per unit width perpendicular to the screen through this particular crack. Okay? This is a question. Think over this question, how to solve this question. This is a tank. Four mm is actually very high value, but still think over it. This is worth 2 marks in your examination. Chaliye. I hope you are able to imagine that. This and this are behaving as two fixed walls. When a crack is developed, the upper portion of the crack and the lower portion of the crack are behaving as two fixed walls. If they are behaving as two fixed walls, whatever is the flow taking place over here between these two fixed walls is basically going to be flow between two fixed parallel flat plates. And the flow is laminar. Don't worry, the flow in these cases are laminar only. Whenever you're going to have these small cracks, you won't have turbulent flow. It is going to be laminar flow only. The flow is laminar over here. If the flow is laminar, now it is time for me to write down some data. This height of the crack is 4 mm. That is basically B. B is equal to 4 mm, or it is equal to how much? 4 mm is equal to 0.004 meters. This is 4 mm. The length of the plates, L over here, length of the plates is equal to 10 centimeter. That is equal to how much? 0.1 meters. The density is equal to 1200 kg per meter cube, and the value of viscosity is equal to 1.2 Pascal second. All these things are known to me. One more thing is indicated over here. The crack is developed at a distance of 2 meters from the interface. That means at this particular point, I'm going to have some pressure P1. At this particular point, I'm going to have some pressure P2. The value of P2 in gauge is equal to 0 because you're exposing it to atmosphere. Now, the value of P1 has to be equal to rho into G into 2 meters. That will give you some value. And the value of delta P will be equal to how much? P1 minus P2. Drop in pressure in the flow is equal to how much? P1 minus P2. It will be equal to something. You will find this particular value. Rho is equal to 1200, G 9.8122. Get me the value of P1 and delta P. दोनों लिखिए आप अपने comment box में. P1 and delta P. How much will it be? Height of the crack is basically the thickness between these two plates is height of the crack. I hope all of you are following this thing. It's a good question. P1 23544. Delta P also should be, of course, same thing. 23544 because the value of P2 is equal to 0. Okay. I hope all of you are getting these values. I hope this thing is clear to you. See, I cannot magnify. Just imagine if I magnify this thing, it is like two plates between which you are having a height equal to how much? 4 mm. This is the upper part of the crack. This is the lower part of the crack. So this is wall portion. This is wall portion. In between, there is a passage left for flow to take place. Flow is taking place over here. This end, I'm having some pressure P1. This end, I'm having some pressure P2. Okay. This is what is happening over here. Chaliye. Now, the formula for discharge. The formula for discharge. Okay. If you don't remember the formula, still at least you have to remember some basic formula, which is a local velocity formula. From there, you can get average velocity and then you can get discharge. Straight away, I'm writing over here. The formula of discharge is equal to 1 by 12 mu delta P upon L, because minus dP by dx is delta P upon L multiplied to B cube into W, B cube into W. So this is equal to how much? 1 by 12 into mu over here is equal to 1.2. Delta P over here is equal to 23544 divided by L is equal to 0.1. B cube over here is equal to how much? B cube is equal to 0.004 cube into width over here, unit width. ठीक है, चलो करो. Give me the value of Q. Oh, come on. This much value of Q, Atul Anil, you won't get. That is a very high value you're saying, but still let us check. Someone please give me the value of Q. Okay, you're seriously getting 0.001 meter cube per second. Fine, probably then Atul Anil, your answer is correct then. ठीक है, 1.0, 1 second, 1.0464, 1.0464 liters per second, ठीक है. Let us take this value, 1.0464 liters per second. See, this is the application of laminar flow between two fixed parallel flat plates. So it is approximately 1 liter per second you're getting. Okay. Chaliye, with this we complete the concept of laminar flow between two fixed parallel flat plates. Let us now move further to the next topic. You can take a snapshot if you want quickly. You can take a snapshot quickly. The next topic. Next topic is very interesting one. It is first of all technically interesting. Second thing, from examination point of view also, what happened was, even though it was there in the syllabus, for more than 20 years, it never appeared even once. Not even once it appeared. Suddenly one year, I think last year, 2 years back paper, they asked one 2 mark question directly from there. Straight away one 2 mark question. Surprise, right? So this topic over here is known as Couette flow. Don't write anything for some time. This is slightly tricky flow. You listen to entire thing. You listen to the entire thing. At the end, everything will fall into place. The moment I start writing and then you start writing, then we will be only, fixed in that question answer thing. Listen to the entire thing. At the end, you will understand perfectly. This topic over here is known as Couette flow. It is known as Couette flow. Someone is asking, one second, someone is asking that the previous question could be solved by using Bernoulli equation. For solving that question by Bernoulli equation, you would be requiring the value of, actually, no, you cannot solve by Bernoulli equation. You cannot solve by Bernoulli equation. That question cannot be solved just by Bernoulli equation. Okay. You will have to go for these equations only. No other option you have. Chali, let us see what is Couette flow over here. Couette flow is a laminar flow between two parallel plates amongst which one plate is fixed and the other is moving. One plate is fixed and the other is moving. Such a flow is known as Couette flow. Imagine, one second, before I start writing those things, take a rough paper and write down the formula for average velocity, write down the formula for discharge quickly. A rough paper, write down these formulas. This is laminar flow between fixed parallel flat plates. Quickly write down the formula for average velocity, write down the formula for discharge, write down the formula for local velocity. Quickly. You have written these three formulas, I hope. Write the formula for shear stress, this formula. Write the formula for shear stress. Okay, write the formula for shear stress also. Chaliye. I asked you to write down 4 formulas: average velocity, discharge, local velocity, shear stress. You already have those formulas, but still write them again. They will be helpful over here. Let us come back now. Imagine that you are having some passage like this. One moment. Let us say the lower plate over here is a fixed plate. The lower plate over here is a fixed plate. The upper plate over here is a moving plate. Upper plate is a moving plate. It is moving with some velocity capital U. It is moving with some velocity capital U. Okay. The distance between these two plates is represented by capital B. The distance between these two plates is represented by capital B. Fine. If I look at the boundary conditions, all of you must be already knowing that the boundary conditions over here, imagine that I take a particular section. If I take this section, let us say this point is certain point M. This point is certain point N. Velocity at point M is supposed to be equal to capital U. Small u. Small u at capital M is supposed to be equal to capital U. And the velocity at N, by the virtue of no slip condition, has to be equal to 0. Okay, fine. Now, if a quid flow is taking place, I'm already having some velocity over here. The velocity over here is equal to how much? Capital U velocity. The velocity over here is capital U velocity. What kind of velocity profile is possible? To understand this thing, you have to understand that there are three types of quid flow possible. There are three types of quid flow possible. Now, first type of quid flow is known as simple or plain or pure quid flow. First quid flow is simple or plain or pure quid flow. What is going to happen in that particular case? The velocity profile is going to be like this, straight line velocity profile. This is the first type of quid flow. This is the first type of quid flow, simple or plain or pure quid flow. The second category of quid flow is known as forward quid flow. Right now you won't understand. Just look at the diagram, accept the diagram. At the end you will understand. The second type of quid flow is known as forward quid flow. How will the velocity profile in forward quid flow look like? The velocity profile in forward quid flow is going to look something like this. It is going to look something like this. This kind of quid flow is known as forward quid flow. Let me write it as second one. The last quid flow is known as backward quid flow. In backward quid flow, the velocity profile is going to look something like this. This is the velocity profile in backward quid flow. This is the third thing you're going to have. So three types of quid flow are possible. First one over here is known as simple quid flow. Second one, forward quid flow. Third one, backward quid flow. Backward quid flow. Okay. Let us now talk about simple quid flow. Let me now concentrate only on simple quid flow. This simple quid flow has some more names. It is also called as pure quid flow or plain quid flow. So let me do one thing. I'll write simple or pure or plain quid flow. In the case of simple or plain or pure quid flow, imagine that I am having some distance y chosen over here, and the velocity over here is equal to small u. Velocity is equal to small u. My aim over here is to develop the equation of velocity, the equation of shear stress, and the equation of discharge. Three things I'm supposed to develop over here. पहली चीज क्या है? Equation of velocity. Second is equation of shear stress. And third thing, equation of discharge. Okay. I want to find these things out. First thing I can say, small u upon y is equal to capital U upon B. Don't ask me how. The answer is similar triangles. Small u upon y is capital U upon B. So small u upon y is capital U upon B. From here I get the equation of velocity. What is the equation of velocity? velocity local has to be equal to capital U into y upon b. Capital U into y upon b. This is the equation of local velocity in the case of simple quick flow. Second thing, talk about shear stress. I can say the value of shear stress has to be equal to mu into du upon dy. Mu into du upon dy. अब देखिए u की value है capital U into y by b. If you do du by dy of this thing, you'll get capital U by b. Therefore, the value of shear stress has to be equal to how much? Mu into capital U divided by b. Third thing over here is the concept of discharge. Discharge is equal to area times, it is equal to area times average velocity. Area times average velocity. Now think about the area. The area over here is supposed to be equal to B times W. B times W is the area. Average velocity will be equal to how much? Logically, you can say average velocity is equal to, since it is a linear variation over here, it is capital U by 2 will be average velocity. So you are going to have over here discharge is equal to average velocity is capital U by 2. I'll write 2 over here, don't worry. Multiply to area over here is equal to B times W. These are the values for simple quick flow. Now these are very simple values. Now I am going to define quick flow in a manner you will understand easily. First of all, you take a snapshot of this particular slide. You take a snapshot of this particular slide. Now you see, look at this thing. Look at this thing. Any quick flow can be visualized as combination of two things, first thing and second thing. दो चीजों को combine कर रहे, superimpose कर रहे, you are combining two things. Which two things over here? Combination of, first thing is simple quick flow and laminar flow between two fixed parallel plates. Laminar flow between two fixed parallel plates. So basically, quick flow is actually, imagine that you are having, look at this particular slide. You are having laminar flow taking place between two fixed parallel flat plates. Now what you do, while the flow is taking place, you remove the fixing over here and you start pulling this plate also forward. Once you start pulling the plate forward, this velocity profile, which is parabolic, will now have this velocity moving with the velocity of the upper plate and still parabolic. What will you get then? Parabolic, but with upper plates motion over here. Are you able to imagine this thing? Are you able to imagine this? One second, let me take a fresh slide, some random slide, let us say. You are having this kind of velocity profile. Then create an animation. Your mind should be very imaginative. You are pulling this thing. As you pull this thing, what is happening? Even he is getting pulled. He is moving like this. He is getting moved like this. Whatever is the velocity over here, he is obtaining that particular velocity. So basically it is a combination. Basically, it is a combination of simple quick flow. Along with that, you are having laminar flow between two fixed parallel plates. Okay, so these two things are getting combined now. If these two things are getting combined, Then I am now going to write down the equations. 3 equations I'll write down. First equation over here I'm going to write down is the equation of local velocity. It is the equation of local velocity. I'm writing. I am telling you, this is the simplest way of understanding Couette flow. You open other books, you will get troubled. Okay. And again, I'm telling you one more thing. I was not taught this way. First of all, I was not taught the fluid mechanics subject. But during our MTech, we used to struggle a lot with books. So after struggling a lot with books, some ideas came in. Those ideas I'm telling you over here. Okay. So this, if you're understanding, you're basically converting a lot of effort into simple effort over here. The formula for local velocity over here, it has to be the formula of local velocity in simple Couette flow plus local velocity in laminar flow between plates. अब बताइए ये कितना है? This, excuse me, this over here is equal to capital U into Y by B plus, what is this formula? Recall कीजिए this formula. Okay, I told you to write down that particular formula. Okay, I can write that formula as 1 by 2 mu minus dp upon dx multiplied to b times y minus y square. This is the formula for local velocity of any Couette flow. For any Couette flow. Now, second formula, let us see. Second formula, let us see. Let us say this formula is for shear stress. This formula is for shear stress. This formula is for shear stress. If I'm looking at the formula for shear stress, then what will the formula for shear stress over here come out to be? The formula for shear stress in simple Couette flow plus shear stress in laminar flow between two fixed parallel flat plates. Okay, so shear stress in simple Couette flow will look like what? Shear stress in simple Couette flow was equal to mu into capital U upon B plus shear stress in laminar flow between two fixed parallel flat plates was equal to how much? It was equal to minus dp upon dx minus dp upon dx multiplied to how much? Multiplied to b minus 2y whole divided by 2. B minus 2y whole divided by 2. Third formula over here is the formula for discharge. This is a formula for discharge. It is a formula for discharge. What should the formula for discharge over here be equal to? Discharge for net Couette flow is supposed to be equal to how much? Discharge for simple Couette flow. कितना था वो discharge for simple Couette flow? It was equal to capital U into B times W divided by 2. देखिए कितना easy है याद रखना. Plus, what was the discharge you are having over here? The discharge you are having over here was equal to 1 by 12 mu minus dp upon dx multiplied to b cube into w. This is what you are having. So now you are seeing that how to combine these two formulas and develop the formulas over here. Okay. Last formula which can be combined. After this, you can't combine any other formulas. You're not supposed to combine any other formulas. Last formula is average velocity formula. You can combine average velocity also. What is the average velocity supposed to be equal to? Average velocity is supposed to be equal to, in simple Couette flow, capital U by 2. In laminar flow, it is equal to 1 by 12 mu into minus dp upon dx multiplied to b square. This is the average velocity of Couette flow. Only 4 formulas you have to remember over here. Only 4 formulas. Now tell me, if I just look at these formulas, पहला part, plus से पहले का part. If I just look at these formulas, these are the formulas for simple Couette flow. That means for simple Couette flow, these values are going to become 0. These values are going to become 0. Give me a logical conclusion that what is making these values 0, which component over here is making these values 0 in simple Couette flow. I wish you were in front of me. Very good, very good, very good, very good. I'm really happy. Okay. Many of you have given me correct answer. Very good. The logical conclusion is, in the case of simple quet flow, your minus dp by dx or dp by dx is equal to 0. That's it. In the case of simple quet flow, the value of dp upon dx is equal to 0. If dp upon dx is equal to 0, then you are going to get any quet flow converting into what quet flow? Simple quet flow. It is going to convert into simple quet flow. It is going to convert into simple quet. Now look at this last slide. Once you look at this last slide, everything will fall into place. Imagine that you are having a simple quet flow plus nothing will give you what? Simple quet flow. It will give you simple quet flow. This is simple. You might be thinking, what is he doing? Plus nothing and all. Don't worry. Everything is going to become easy now. Second case, forward flow. Don't mind my handwriting now. It is very difficult for me to write neatly now. Is simple quet flow plus laminar flow in the same direction. You see, this flow is also in the same direction. This flow is also in the same direction. You are now supposed to get forward flow. You are now supposed to get forward flow. You are now supposed to get forward flow. I hope you are able to conclude what is going to happen in the next case. Backward flow कैसा आता? मेरा ख्याल है आप लोगों को समझ में आ रहा? How will you get backward flow? Simple quet flow. Simple quet flow यहाँ पे है. But laminar flow is taking place in backward direction, in this particular direction. Then you are going to have backward flow. You're going to have backward flow. If simple quet flow and laminar flow between plates are in same direction, you'll have forward flow. For this thing to happen, the value of minus dp upon dx should be positive. For this to happen, minus dp upon dx should be positive. And if simple quet flow is taking place in forward direction and laminar flow is taking place in backward direction, you are going to have backward quet flow. So this is minus dp by dx is equal to negative. I can't tell any simpler now. This concludes the concept of quet flow. I hope it is clear to all of you. I hope this is clear to all of you. See, dp by dx equal to 0 is by the virtue of pressure difference between these two ends, the flow is taking place. Okay, but that is not happening over here. Over here, dp by dx is equal to 0. That is not happening over here. Over here, flow is only taking place because you are pulling this plate. See, there are two things driving the flow. One is pulling the plate and one is the pressure gradient. Over here, pressure gradient is not there. Only pulling the plate is there. That is why the flow is taking place. Over here, pulling the plate is also there. Pressure gradient is also there. Both are combining over here. Over here, pulling the plate is there. Pressure gradient is in the opposite direction. Therefore, this combination is coming over here. Means head loss is equal to 0. No. You can't say head loss is equal to 0 in simple quet flow. Head loss will be present over here by the virtue of the shear stress developed in this particular case. Okay? This is all you're going to have in the case of quet flow. Fine. So remember this concept that when dp by dx equal to 0 simple, when minus dp by dx is equal to positive forward, when minus dp by dx is negative, you're going to have backward flow. And these are the formulas. Only these formulas can be superimposed. No other formula you're supposed to superimpose over here. Now take one question that appeared in examination. The question for 2 marks, this appeared. Now you see for 2 marks such simple question. But this question would not be as simple if the understanding was not clear. The question is, identify the value of minus dp by dx for which discharge in co-wet flow is equal to 0, 2 marks. But before you answer this thing, anyone can answer this now. That is not difficult. Before you answer this, give me a logical conclusion that whether it is belonging to simple, forward or backward. This question is belonging to simple, forward or backward. Logically सोचिए और answer कीजिए. It is belonging to simple, forward or backward. Very good, Anil. Very good, Pawan. Very good. आबिद गलत आंसर है आपका. Shivin Shahid, correct answer. Very good. It is going to be backward only. You see, discharge should be 0 का मतलब क्या हुआ? Discharge should be 0 means some portion of flow is forward, some portion is backward, which is belong to the third case. Then only the discharge is going to become 0. Chaliye, identify the value and give me the answer straight away. What is the value of minus dp by dx? Get me the answer. You know where to get the answer from. Use this formula, the third formula over here. देखिए, the formula for Q was equal to how much? UBW divided by 2 plus minus 1 by 12 mu नहीं plus था ये plus 1 by 12 mu minus dp upon dx multiplied to क्या है यार b cube into w ना this value was there. This was there. So the value of 1 by 12 mu minus dp upon dx into b cube into w must be equal to minus ubw divided by 2. So minus dp by dx has to be equal to minus 6 mu into u divided by b square. Check कीजिए. Okay, minus also is supposed to be there, no? Very good. Minus also is supposed to be there. So it is belonging to backward flow. Okay. In place of discharge, if someone says shear stress at wall, if the question in place of discharge, if the question is shear stress at wall, then tell me what is minus dp by dx equal to. Chaliye, try this question. In place of discharge, if the question is shear stress at wall is 0, then minus dp by dx is equal to how much? At fixed wall. Come on, are you trying? Shear stress at the fixed wall is 0. Minus dp by कितना रहता? नहीं यार, आप लोग ट्राई नहीं कर रहे. Very good, Uday Kumar. Very good. B square आना चाहिए. Check Uday Kumar. It should be B square. If you check this value, should become equal to -2 mu u upon B square. If you are not getting, try it again. You will get later. Okay. This is regarding the concept of Couette flow. Next thing, last topic. Within 2 minutes, it will finish off. The last chapter, last topic of this chapter is known as creeping flow. This is known as creeping flow. This is known as creeping flow. How do we define this creeping flow? Highly viscous flow. A highly viscous flow in which the Reynolds number, R should be capital over here, in which the Reynolds number is less than or equal to 1, less than or equal to 1. That is known as creeping flow. Since this flow obeys Stokes' law. There is a particular law called the Stokes' law. We'll discuss what it is later on. Stokes' law. Therefore, this flow is also known as Stokes flow. It is also known as Stokes law. Now, what is the Stokes law? Stokes law, we are going to discuss again later on in the chapter of drag and lift. Stokes law basically says that the value of drag force is equal to 3 pi mu d into u infinity. This is known as the Stokes law. We'll discuss this formula again. Civil people might be aware of this thing from environmental also. From this particular formula only, you're going to get the concept of settling velocity. You might have seen the concept of settling velocity was equal to 1 by 18 mu density of particle minus density of fluid multiplied to g times d square. Settling velocity concept, settling of impurities in water, all those things you have. Right, that formula actually, this particular formula is actually coming from the Stokes law only. It is coming from Stokes law only. Okay. So example of creeping flow is settling of impurities. Settling of impurities. Flow of dust particles. Dust particles. These are some examples of creeping flow. Okay, regarding this, more detail will be there in the last chapter called as drag and lift. Right now, only this theory is sufficient for you. Okay. So today's class closes at this thing. We have finished off the chapter of laminar flow. Okay, to summarize, we are having 4 concepts: laminar flow through pipe, laminar flow between fixed parallel flat plates, Couette flow. I was expecting you to respond better in Couette flow because these two slides should be sufficient to understand entire thing. But if you are still having difficulty, go through the slides once. I'm telling you, more than this, I cannot clear anything. Everything is spoon fed over here. This diagram especially is spoon feeding only. Okay, you go through Couette flow, and last one is creeping flow. Creeping flow is not at all important for you at this stage. ठीक है? This completes the concept. I'm going to take some questions now. Swarangi Marathe. Hello, good morning.
Hello, sir. Good morning, sir.
Good morning.
Sir, I have a doubt in one question. The question is a hollow sphere of inner radius 80 mm and outer radius 90 mm. Floats half volume submerged in an oil of density 800 kg per meter cube. And they are asking mass of sphere and specific gravity of sphere.
Density of fluid?
800 kg.
800 kg per
meter cube.
Okay, so what is the doubt in this?
Sir, I got the answer, but it is coming wrong.
Sorry. If you are getting the answer, chaliye. Now the volume of fluid displaced is equal to how much? It is equal to half the volume of sphere, outer sphere.
Yes, sir.
Outer sphere.
So only outer sphere will consider.
Half the volume of outer sphere will be the volume of fluid displaced now.
Okay, I considered 4/3 pi r inner radius minus outer radius minus inner radius.
Tell me, is this portion? Tell me, is this portion? This portion, you're 1 second. Tell me, is this portion filled with oil or it is hollow?
Hollow.
Hollow. That means that portion also, water or oil was there, that also got displaced.
Okay.
So kitna fluid displaced over here is equal to how much? This entire portion fluid is displaced. This is the volume of what? Outer sphere's half.
Okay.
Imagine, madam, that you are having diagram over there was very small. Now try to imagine like this. Okay. Okay, sphere is only this portion. Sphere is only this portion. But tell me, volume displaced of fluid is how much? Is this portion where are you seeing where my cursor is?
Yes, sir.
Is this portion having oil or not? No.
No, it's not having oil.
That means that this volume also has been displaced.
Okay.
So volume displaced is equal to half the volume of outer sphere. No?
Okay.
Try this.
Yes, and while considering weight of body, I'll consider
that time what you are doing is correct. 1 by 4 what do you call?
4/3 pi.
वो outer minus inner वो सही है. Outer cube minus inner cube वो सही है. ठीक है?
Okay.
That is the volume of sphere उतना है, accepted. But volume of fluid displaced उतना नहीं है.
Okay.
Volume of fluid displaced is this amount of volume. It is the hemisphere of outer sphere. Okay, no?
Okay, sir, got it.
Okay.
So one more question is there.
Tell me, ma'am.
Sir, a wooden cylinder having a specific gravity of 0.6 has a concrete cylinder of the same diameter.
Okay.
And 0.2 meter length attached to it at one end.
At one end. Bottom or up, he did not say.
It is length of concrete cylinder, sir.
No. The concrete is in the bottom or upper. He did not
mention. Bottom.
Okay, fine.
The specific gravity of the concrete is 2.5. And the length of the wooden cylinder for the composite block to float vertically. It is asking.
This is how much? Concrete is how much?
0.2.
0.2. This is water?
Yes, sir.
Okay, what is the difficulty in this thing?
Let us. In this wood will come up now, like it will
Why
float.
Will it come up? But it is composite body, na madam. It is composite body. This composite body, if you see, it is having a combination of a lighter body and a heavier body. It is having a combination of lighter body and heavier body. It is now a composite body. It can float down. Is it not?
Okay, I consider that wood will be half up and half down, like.
No. Imagine you are attaching. Okay, you are attaching something which is very heavy. I am getting a funny kind of example over here. You might have seen in some kind of movies that people, while throwing someone into a well or something, they'll attach a stone and throw. Now that person is having a lighter density than water in general. Yes. But when you attach a stone, then he will submerge down, then he'll die. That's funny kind of example, but relevant still over here, right? So since you're attaching something which is heavier than water, there is a good possibility of wood also getting submerged because he's now in contact
He is now in contact with this thing, is it not?
Yes.
So he can submerge. He might or might not, but the question is saying he's getting submerged. Then you consider submerged and find the value of length. If the question says some portion is left over here, then consider that and then go forward. Okay, na?
Okay, so then I can solve it, sir.
This is a very simple question.
Yes, sir. Okay, so thank you.
Thank you. Tej Kulkarni.
Hello, sir.
Hello, tell me.
Sir, in the first slide, sir.
First slide. First slide is yesterday's slide, na? Tell me.
Today's first slide. Sir, in this rotation, sir, next slide, I think, sir.
Okay.
In that points you noted down. In that, I did not understand that point of rotational flow.
You're having a velocity profile something like this. You're having, let us say, a particle over here. Upper layer moving with higher velocity, lower layer moving with lesser velocity. Tell me, the fluid particle, will it translate purely or rotate and move forward?
Sir, I think, sir, it's laminar flow, so it should translate, sir.
You won't tell me it is laminar flow. I'm telling velocity profile is parabolic. Upper layer 5 meters per second, lower layer 2 meters per second. Okay. Tell me, how will it move? Will it move as a straight? Will he become like this later on, or will he become like this later on?
Yes, sir. Sir, but it's not a single body. It's a continuous body. So infinite particles. So they should not.
Infinite particles. All infinite particles will start rotating them. All the particles. This is velocity profile is given actually for this particle, then this particle, then this particle. Velocity profile is not defined for all these things over here. It is defined for a particular section particles. Okay. Upper layer having more velocity, lower layer having less velocity. Tell me, will it move? Tell me then, can it rotate or not rotate?
Yes, it can rotate.
It should rotate actually. As a matter of fact, laminar flow is highly rotational flow. Okay, highly rotational flow. You can also get the value of omega over here. The value of omega is equal to how much? Because what is the formula for omega? About z-axis. Remember omega about z-axis? Hello?
No, sir. No.
1 by 2 dou v upon dou x minus dou u upon dou y. V is not defined over here. Only u is defined. Is u having a variation with respect to y? See, minus dou u by dou y is actually equal to dou u by dou r. It is equal to dou u by dou r. How is it so? How is it so? You see over here. Now, what is the relationship between, look at this slide. What is the relationship between r and y? R is equal to capital R minus y, correct?
Yes.
You differentiate on both sides. Capital R is a constant.
Yes.
Are you following or not, sir?
Yes, sir. Yes, sir. Yes,
capital R is a constant, hai na? Capital R is
yes,
a constant.
Sir.
So you'll have dr is equal to minus dy, correct?
Yes. Sir.
If dr is equal to minus dy, you can replace minus dy by dr. So basically, omega about z-axis in the case of laminar flow is equal to half of dou u upon dou r. Dou u upon dou r. You know the value of dou u upon half. This is half, okay? You know the value of dou u upon dou r. How? U is equal to how much? 1 by 4 mu minus dp by dx multiplied to capital R square minus small r square. From here, you can get the value of dou u upon dou r. From there, you can get the value of omega about z-axis. This can also be a question in examination. Find the value of rotation in the case of laminar flow through pipes.
Okay, sir. Got it.
Okay, no? Fine.
Thank you, sir.
Thank you. Anyone having doubts? Yes, Shankar.
Sir, will the syllabus will be completed within next week, sir?
Are you from civil or mechanical?
Civil, sir.
Civil, hopefully, exactly this day next week. Hopefully, syllabus will be completed. Hopefully.
Okay,
Or
sir.
at maximum, I'll have to take Monday for civil. For mechanical, I'll have to take more 3 days.
Okay, sir. Thank you, sir.
Saurav Kumar.
Hello, sir.
Yes, tell me.
At last, we have written a U infinity. Sir, that is settling
Achha,
velocity.
that u infinity that you will understand later on. It is called as free stream velocity. This u infinity is called as free stream velocity. You'll understand this later on. In the chapter of drag and lift, this u infinity will come. It is called as free stream velocity. Don't worry now. Just remember the formula. In drag and lift, we'll consider this formula again.
And
Okay.
sir, for finding power loss, so you said something that we shouldn't use that formula for head loss, including average velocity.
See, if you take average velocity, then what will happen? The formula for power loss will have V as well as Q. It will have V as well as Q. Okay. Either you'll have to convert Q in terms of V or V in terms of Q. Then you will get the same thing. See, you can use it. You can use the formula for head loss from velocity concept and just say gamma into Q into head loss. This is also fine. But the problem is this head loss is having V inside, na?
Yes, sir.
तो V भी आ जाएगा, Q भी आ जाएगा. उससे अच्छा है कि सिर्फ Q को रखोगे तो Q स्क्वायर बनेगा. आसान हो जाएगा आपको. Are you following?
Yes, sir.
Okay.
Yes, sir.
Thank you.